Yes, welcome back. Okay, so we were talking about sampling, basically splitting your data set into training and testing parts, and then now we are loading it using data loader. I won't be going into it much. I've already shown you how it looks. You can check out the other streams if you want. I can just show you the length of the whole thing. That's it. Okay, so it apparently has 15 and 4, right? So what is 15 and 4? Basically these are 15 batches we have, and batch size is being 16, so it can be like 15 into every single one has 16 of them, so it is 2 or 40, which is the number of elements in the training set. And right, and for the testing set it has 4, so 4 into that is 64. So basically your validation set has 60, so 4 of the last batch will have 4 less, right, than this one. So the last batch will, so basically last batch will have 12 in them, right? Cool. Done. Data set is loaded. Let's go in. Okay, now we have the extrain extensor, that is the actual tensor, and we are getting the index out of it. So you see, this is the extensor, right? So this is basically all of them. Yeah, so that is that. And okay, now I'm getting the indexes out of it, right? So indexes is what? Basically all the indexes, that is 240 of them, and I'm getting all of them. So if I see, so basically the splitting is happening actually here. If I see the shape of this, it's 240 comma 1 comma 5 comma 5, all that stuff. So we are splitting the whole thing here. Again, validation set, this same thing is happening. We are using the index to split that whole thing. Okay, and then we are creating a composer. This is for training. We are flipping it horizontally and also normalizing it. I mean, there's no need to flip it horizontally or whatever in this particular case. It's just to showcase the whole thing, right? So that's it. Okay, cool. So we performed the split. Okay, and we have different composers. So we are not flipping, we are flipping. See, the thing is, data augmentation is a part. What is data augmentation is, you change the data so that you create more data out of it. In a sense, we can do that because especially with images, right? You have an image of a dog, you can zoom into it, you can flip it, you can distort it a little bit, change the color palettes, or maybe you change all these, hue and contrast and all that. If you change them also, you have a new image. If you crop the image, it's also a new image. And if the dog is there, then it's still a valid image to do the classifications, right? So you can do this data augmentation to create more data from your existing data. So something like that can also be done using this compose methods, right? Okay, if you do not perform data augmentation, you may keep using samplers and single data sets. Okay, and do all that. So cool. Let's initialize both of them. Okay, transform. This is what we have done, right? You remember, it gives out your x and y and all that stuff, right? I mean, it's pretty chilled out. Okay, trainer, build a loader out of it. Okay, the loaders are built finally. Okay, so here is our actual thing happened. Okay, till this we were just showcasing how things are working. Here we have done the splitting and initialize the transformation that you need to do, create a data set, and then data loaders. Okay, now everything is Perfect. We can also see trainer loader. What is this? It is a class of data set. And you can see next comma iter comma data set. Okay, I can do that. I can also do with train loader, right? train loader, right? Yeah, yeah, I got that right. So if you check this out, I think I'm getting 16 of them, right? With the labels included. So this is the first one, and also the label that is given to the first one, that is 0, that is it's a straight line. Okay, works. Okay, now let's talk about weighted random sampler. Okay, so we have already talked about imbalanced data set, right? When learning about binary cross entropy in basic uh, classification that we did using logistic regression, we adjusted the loss weight for points in the positive class to compensate for the imbalance. It wasn't quite the weighted average one would expect, though. Now we can tackle the imbalance using a different approach, a weighted sampler. The result is pretty much the same, but instead of weighted loss, we use weights for sampling. Okay, so basically we are giving more weights to the class which has less samples in the dataset, and less weight to the class which has more frequency in the dataset, right? So the class with fewer data points, that is a minority class, should get higher or larger weights, while the class with more dataset, the majority class, should get smaller weights. This way, on average, we will end up with a mini batch containing roughly the same number of data points of both the classes. Okay, so now how are these weights computed, right? The first, we need to find how imbalanced the data set is, that is how many data points belong to each class. Okay, we can simply use PyTorch unique function to on the training data set, right? And it will just return the counts of all the unique ones that is there, so we will know how many are there in the what do you say, the positive class, and how many there are in this negative class. So let's see that. Let's run this one. This goes here and this goes here, and you can see the terminal. So right now there are unique is 0 and 1. So we are doing it on the label. If you see y, we are using the y, that is the label part of the training set, and we see there are 80 instances of class 0 and 160 instances of class 1. So you can clearly see a pretty big difference. That is basically saying the binary class here is the zeroth class, 0 being that they are straight and 1 being they are diagonal. Okay, yeah. So let's count. So ours is a binary classification, so it is no surprise we have two classes like 0 and 1, right? There are 80 images with lines that are not diagonal, and 160 images with lines that are diagonal. Okay, so now weights we can compute by inverting the counts in a sense. So think of that, if mathematical intuition would be something like uh, mathematical, like if your weight is high, right? If your let's say your weight is higher, so the reciprocal of this weight will be lower, right? So and vice versa, right? If your weight is lower, then the inverted function of that uh, weights will be higher. That's what you are on, right? The class that is in minority should have more weightage. The class that is in majority should have less weightage. So we will just simply do this simple straightforward operation where you are just doing this weights, inverting them. So weights are being calculated simply using that. Okay, weights are being calculated. So let's see what the weights are. Weights, and you see the weights are 0.01 for the zeroth class and 0.0062. So what was in majority? The one was in majority, so you see the weights for one is much less than the weights for zeroth class, right? uh, yeah, that's more like it. Cool. Okay, let's go forward and sample these weights. You have the weights. Okay, you weights is a list right now, right? And you are taking the white rate and squeezing it. You know what squeeze is? You are reducing one dimensionality. So for visualization, it has a shape of this guy, and if we squeeze them, it will become a 1D tensor, basically an array. So that's an array. If I do a shape on this guy, it will be shape. Okay, yeah, see, it became 1D array from a 2D array, right? And the log is basically to have that floating points, precisions, and all that stuff, right? And now what happens if you do this, right? This whole thing, that is this thing, you are indexing on the weights, right? So if I take this now, as I already run that, right? I have already done that. I can see for myself. So now it's up for that index, which was supposed to look like this. So for 1 is being converted to 0.0063, and all the zeros are converted to 0.125. So you kind of gave a weight the whole thing, you know, and we can see how they look like. Weighted samples here and here. Let's see it here in the terminal. So you see the shape of the is 240. This is how like the first 10 samples would look like, and this is your white train samples with a squeezed one would look like. It was like this before, but now you see there's 0 here, so that part is 0.0125. Cool. Okay, let's use a generator. It's a PyTorch generator. Okay, we can I'll go to that. So what you find is the first weight, that is 0.0125, correspond to the negative, not diagonal. That is, since the class has 80 out of 240 images in our training set, it is also the minority class. The other is the majority class, right? So the minority class should have the largest weights, and I already done that. So each point belonging to it gets over represented to compensate for the imbalance, right? But these weights do not sum up to 1. Isn't it wrong? Right? These weights are not summing up to 1. Just so you know, the weights are right here. This guy. If I do a sum on this, it's not 1. Isn't it wrong? Because we want to keep it in the probability kind of a thing, right? Happening. It is common to have weights summing up to 1, sure, but this is not required by PyTorch weighted sampler. We can get away with having weights inversely proportional to the count. In this sense, the sampler is very forgiving, but it is not without its own quirks. Okay, it is not enough to provide a sequence of weights that correspond to each different class in the training set. It requires a sequence containing the corresponding weights of each and every single data point in the training set. Okay, even though it is a bit annoying, it is not so hard to accomplish. We can use the labels as indices of the weights we compute above. It's probably easier to see it in the code, right? So let's do that. We already did that actually here, right? This guy, where I showed you how every single weight, every single corresponding weight has to change in the data set. Cool. Okay, cool. The sequence of weight is the main argument used to create the weighted random sampler, but not the only way. So let's look at the argument. So we will look into it, how it's happening. Okay. Okay. You create a generator. We'll explore what it does. So you have a sampler, and we are importing weighted random sampler from PyTorch. Okay. You have the samples, the weights of the samples basically, and the length of the whole thing, that is 240 as of now, right? So, and this thing is passed as a weight sample weights. and the generator, okay, it's like, I guess, to generate the whole new thing. And is replacement is equal to true. So okay, it's going to use the same image twice, right? So let's see what these parameters are. So weights, a sequence of weights like the one we have just computed, right? And number of samples, how many samples are going to the withdrawn, typically the length. Now replacement true draws samples with replacement. If number of samples equal to the length equals the length, so number of samples equals the, that is, if the whole training set is used, it makes sense to draw samples with replacement to effectively compensate for the imbalance. Does that make sense? Because so like, if your whole training data set is going into it, if you want your minority to be your majority, so you can do the replacement, that you can use the same data twice, right? So it will be more. So that's what we mean by, so it makes sense to draw like samples with replacements to effectively compensate for the imbalance, right? It only makes sense to set it to false if the number of sample is less than the length of the data set. Okay, cool. Now generator, optional. It takes a pseudo random number generated that will be used for drawing the sample. To ensure reproducibility, we need to create and assign a generator which has its own seed to the sampler, since the manual seed we have already set is not enough. Okay, cool. Okay, so we are going to sample from the whole training set, and we have our sequence of weights ready. We are ready. We are still missing a generator though. Let's create our own generator. Okay. Didn't You may ask that, didn't you say that we need a set of seed for generator? Where is it? Indeed, I said it. We will set it soon. After assigning the sampler to the data loader, we will understand the reasoning behind this choice, and all that's things, right? Okay. Sampler is there. We are putting it in the data loader. Data loader is there, and we are using the sampler here. Okay. Okay. Data loader comes with an argument. Okay. Pretty cool. Pass it here. Pass it here. Okay. I guess it's done. Once again, if we are using a sampler, we cannot use the shuffle arguments. Okay, there is a lot of boilerplate code here. I know. Okay, so make balance helper. We will just do all that stuff in a single function. We are creating a function for everything. That is counting the unique ones, creating the weights, creating the samples out of the weight and generator, and then actually sampling out from our data set. Okay, and then the sampler is ready with you, and all you have to do is pass the y train value, the label values, to get the sampler. Okay, and that it does perfectly, and here it goes. Done. Okay, let me see the what is sampler is a argument. Sampler is an instance of weighted random sampler that will be used in the future. Seeds and more. Okay, we'll go into that. Okay, time to set the seed for generator used in the sampler assigned to a data loader. It is a long sequence of objects, but we can work our way through it to retrieve the generator and call it manual seed method. Train loader sampler dot generator dot manual seed 42. It's a long name, and we are setting all the seeds. Okay, and let's see what this. Okay, now we can check if our sampler is doing its job correctly. Let's have it. Mm, mm. Yeah, so let's see. let's have it sample a full run, 250 data points in 50 mini batches of 16 points each, and sum up the labels so we have how many points are in positives class. That's what it is doing. Okay, it's taking the t from iter. So if you take iter of train loader is a tuple where the first part is the feature and the second part is the label. So we are taking the second part, the label, and we're adding them up. Basically, the label whose values are positive, that is 1. We are adding them all up. So if I run this, if I go, okay. Oh, it's going through the whole thing. Okay. I'll just do this. Wait. It's going through this every single one of them. I'm gonna where is it? Where is it? Where is it? Where is it? Okay. Here it is. Okay, I'm gonna run this like this. Okay. Hmm. I could have just run this here. And here we go. Here we go. So right now there is 122 samples that are positive in nature. You see, what was it before? If you remember, it was uh, 240, 60 then when we were trying to find, right? Gave it a weight. I forgot exactly. How much was it? Yeah, it was 80 and 160. So 80 of them were 0 and 160 of them were 1. So right now there are 122. So they reduced from 160 to 122, and hopefully the other guy also has almost the same amount. Let's see. Okay, okay, that's just weird. Mm, give me a second. I'm making some kind of mistake here. Okay. Okay. I guess I made a small mistake here. Mm, mm. Oh yeah. So right now I guess there's some mistake, but what it's saying is we have 160 images of positive class, and now thanks to the weighted sampler we are sampling like only 123 of them. It means we are oversampling the negative classes that had like 80 of 80 images to a total of 117 images, adding up to 240 images. Mission accomplished, right? Okay, that's it. Okay, it's better to be safe than sorry, and let's do all that things and add it right in the step by step function. This is basically all the seeding methods you can for representatively, and I'm gonna be skipping through them. Add that to the step by step function that we created from the previous sessions, I guess. Putting it all together. Let's go. Okay, skim through this as fast as possible. Images are there. They have 300 images. You are turning them from 0 to 1 to 55 range to 0 to 1 range. That's it. You are reshaping it, the labels from 1D to 2D tensor. Done. Yeah, using index splitter, right, to generate the training and validation sets using some kind of a random splitting. Okay, and convert them. Now you are actually sampling from the dataset. You actually you did that change through the indexing randomly first, and now you're actually indexing on the data set. Right? Build different composer for data augmentation on training sets. Okay. Train has a different composer. Validation has different composer. Right? And what else? And what else? Train data set, validation data set. Both of them coming in. Then sampler, make balance sample. Right? Data loaders are being loaded, and pixels as features. Let's see what we have here. Seems nice. So you have this train loader, right? Let's see what it looks like. Let's leave one by one. This guy looks like this. I can see the shape of this. 16 comma 1 comma 5 comma 5. So data loader, what it does is creates a batches, right? So our batch size has been 16, right? So one batch size, that is next to or blah blah blah. It, I told you, it returns a tuple of x and y, that is your features and labels. So this is your x and this is your y, and we're just analyzing it. So this x will have 16 images as of now, because it's a batch of 16, right? And y will also have like 16 labels for those 16 uh, images, right? Cool. And we can see the shape of it. That's all good. And now we are going to flatten the whole thing. Let's see what happens when you do flatten. Actually, let's do this. Okay, flattening is basically turning the whole thing into this. That is, you actually multiply all these other guys except for the number of images. Number of images has to be same, right? So what you do is you multiply these dimensions into one dimension, that is 1 into 5 into 5, that is 25. So now think of this. The image that you had, that was 1 cross 15 cross, one of the images, right, which 1 cross 5 has turned into just one big array of 25 numbers. I mean, it does not make intuitive sense. Why is it that, or why do you need it? But apparently, it kind of uh, basically you are turning your image data into a vector that you can use as a feature, right? So basically, you can think of this. Now, these 25 numbers are like a feature in a table, like in a CSV file, right? If you remember, if you are doing any kind of regression or linear regression, you have this, right? You have this data set, right? Blah blah blah, and then you have this value part here, and we have all these are called the features, right? When we flatten this whole image, this is 5 by 5 image, into an array of 25 numbers, you can think of this as 25 features are here. Okay, now you have 16 images, right? So now think of them as a table of 16, right? You can think of this as a table of 16, and this is like 25 of them here, and then this is your label part. Okay, and there are 16 of them in one batch. 16 of them in one batch. This one line is representing one image. Okay, cool. And this guy is also representing the label of the image. The first image might be 0, whatever, I don't know. You flatten the next image into this one thing. All the images, that is the 16 images. So now you have 16 cross 25. That is what? That is your x, and 16 comma 1 is your y. Don't we have a simple spreadsheet kind of a thing that we can use to do some kind of classification. Now I have to create what? I will have to just create a neural network with 25 inputs. So it will be 25 inputs, right? All the way to 25. And then I can add whatever the hidden layers are there, shallow, deep, whatever, and then have one node at the end, which I can use to do some, which I can put to the uh, softmax, right? And see if it is 1 or is it 0. I hope that made sense. Something like this, right? I guess we have been using 5 of them, something like this. So it will be like this. So this is the input, this is your hidden layer, and this is your output. Okay, cool. We will be making that right now. Shallow models. We have set a learning rate. I have to explain all that stuff, right? Learning rates tell you how fast you want to converge to the optimal state of the loss function. Okay, let's create a model, your logistic regression model. First part was to flatten. The image is coming as 16,1,5,5. You have to flatten it. Let's add it flatten. We saw how it's doing it. And as I said, the first layer will have what? Input is 25. Okay, right now the and the output is 1. So right now our model looks something like this. Okay, this model that we have just run on the code, okay, that model looks like this. There are 25 of these guys, 25 of them, and then one more. That's it. This is your model, literally. Okay, and then a sigmoid function is added here. We can think of them. I can literally say that it's sigmoid here. Okay, model has been created. Let's see how the model looks like. You can do the state dict, right? You remember state dict? Yeah. So you see output weights is how many of there are there? Pretty simple to calculate, right? It's 25 into 1, 25 of them. So there are 25 weights, and we don't have any biases because we haven't set bias equals to true. If it was true, then it will add one more, so it will be 26. Okay, I mean that's pretty self-explanatory. Okay, cool. Now let's create our optimizer. We have this parameter thing. So parameter is basically the parameter, the weights that you see, right? If I show you, it tells you it's a, if I go, I think you can also do state dict on that. Stat. How do you do that? I forgot. I think you can go like output dot weights. Can you? No. Okay. What it basically is it tells you it has a way to show the parameter. That's it. Oh, like, yeah, parameters. So this is your model, right? The model starts with a flattening, that is flatten dimension 1 and whatever that is, yeah, and then output, the in feature is 25, input, the output is 1, and all that stuff. Okay, so this has access to all the state that you have in the okay, I can actually go inside them if you think. Let me just see if I can do that. Flatten. I mean, these are things that you flatten. Let's say, can do that. No, we cannot. So as a dictionary, they cannot do. I cannot find that. Okay, we will look into that. But simply it says stating it has the access to all the weights, the parameters. This function is giving that. Okay, cool. We are setting what we are telling is what is optimizer. It optimizer is the algorithm or like the gradient descent, right, which helps you find the um, do the backpropagation and find the loss and optimize the loss, right? And then you have the loss function, that is BC loss, binary cross entropy. We are not using binary cross entropy logit loss, which has a sigmoid already attached to it, so you don't need to have this final layer of sigmoid if you are using that loss. Okay, number of epochs there. Let's start with our initialization. I'm going to run by one so we can really see what's happening. So we are passing in the model, the loss function, and the optimizer that is already there. Let's go inside. You are passing all that and initialize them. Of course, you created instead of a class, so constructor has been called. The basics, right? Model has been set. We're sending the model. If you had CUDA, I don't have. So train loader validation, we have nothing set right as of now. Loss function and validation loss function and total epochs, all that counting will happen here. And now we have instance for this function, that is make train step function. Okay, they created make step function, perform training step, initialize it. Okay, so make train step function actually returns another function. So this is what we call a higher order function, and this function we can use and we can pass the x and y labels and it will do all that stuff. So right now, if you check, if you go inside, so train step function, you will pass to them this guy, you will pass x and y values, that is your batch. Okay, and so is for the step function, the same thing, literally the same thing. You can go inside, see it's written another function, but it's not doing any training, but it's just doing the inference, the prediction part, right? Cool, initialization is done. Let's go next, set loaders. Now what set loader does, it takes the loaders and just set them up like this, and you have train. As soon as you hit train, let's see what happens. Once you go inside train, you pass in the number of epochs you want to go through. It's going in the train. Now this train function has all the make step, train steps and all that stuff all inside it. So now the bigger loop is our epoch loop, right? You have set the seed and all that stuff. I'm not going through that. Okay, yeah, this is your set seed, we defined it, right? All the seeds that you have. Then epoch is there, you are adding to the epoch. Oh yeah, mini batching. So what did you pass? Did you observe that you passed to the whole model? Is it okay? Train, give me a second. Yeah, you're here. You haven't passed anything actually as of now. We're just setting things up. Loss, if validation, no, it's not validation, it's not there. Then data loader is what? Train loader. And step loader, step function is basically your train step function. That is these are functions actually, you remember, these are functions inside the this is a function inside it, right? You can check this out. Sorry, yeah, set loader, you see already set, we have it inside. And this is also a function we have initialized. You remember it's a big class, right? It's a pretty huge class. If I can show you the layout of the whole thing, it's right here. Okay, yeah, check this out. It's a big function with initialization, has all these things, and then two set loaders, tensors. So now make train step function is doing the performance of stepping into the function and doing the trading. This is doing the inference. Then the mini batch is where validation and all the taking the mini batch and doing the training basically. And this is the ultimate one function that controls all other functions in essence. Cool. Let's go through them. Let's go through one by one. You have initialized it, mini batch. Okay, now the batch will happen. Okay, go here. You have the data loader. Data loader has been given to you. I can also show you what is data loader. Data loader is there. It's this guy, and I can simply do the next and data loader. As of this is actually train data, so this is what it is, right? And cool, it's a batch of 16. So let's go how it happens. I'm going to go through one of them. We are getting if transpose, yes, because we are training, we are doing the transformations, we are returning x and y values for 2, 3, 4, x 1, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Then, okay, yeah, we went through every single one of them and we got them. Okay, I mean, that was pretty cool to watch. Um, yeah, okay, so X batch is done. Just like that, we will do the Y batch, and Y batch is also done. Now let's do the step function, that is basically going inside your training loop. You pass X and you are passing the Y. We are setting the training mode, doing the forward propagation, putting through the loss, calculating the gradients for each weights, that is 25 weights of them right now, and then updating the weights, and then removing all the gradients, right, and then returning the loss for this item. Okay, we got the loss, mini batch loss. So now we have trained our model on the first 16 images. Okay, and we have got one loss out of it, and we are appending this into the mini batch loss. Okay, now there are 15, so this will happen 15 times actually, because there are 15 batches, right? So I'm gonna go 15 times. Second time done, third time done, fourth time done, fifth time done, sixth time done, seventh time done, eighth time done, ninth time done, 10th, 11, 12, 13, 14, and here goes 15. Cool. And we are meaning the whole loss and returning the loss. So this is our training has been done on at least the on the whole data, training data once. Now we're gonna do it more because epoch is gonna happen, but we will, before that we have to validate, right? So we'll do a little bit of, this is the same process. You mini batch the validation set in this case, and then you do a forward propagation on the model that has been trained on these 240 data set of the X train, right? And for the first epoch, right, and you add that up, that's it, and you write it down. Okay. Now for the next epoch, there are 100 epochs if I remember right. So this whole thing will happen like 100 times, and we are keeping track of all the uh, necessary information. Okay, I'm gonna stop the whole thing here itself. I'm gonna do the training here. Okay, yes. Is there anything else? Should I be focusing on something else? You know what, let's just end this if I can. Training is happening. Is there any information being printed here? No, nothing much. Okay, training's done, right? And here you go, everything is done. Let's jump into the next part, that is plotting the graph. Oh, okay, I shouldn't have done that. Okay, let me do this once more, putting it all together, voila, whole thing. uh, Feature scaling created. Okay, put it this guy, and okay, I should have just done this. BCE deepish model is where we are gonna go next. Yeah, this is what it is. Brilliant. You can see how the training loss and validation loss is changing. So training loss is in blue and validation loss is in red. Uh, it goes down. It goes down for a little while for like 20 epochs. By that, then it really does not have any good effect. Training loss seems to drop a lot at this epoch, but still then it goes high. So not that great of a model actually. Of course, that's how it's gonna be. We are just using a linear model with no activation as of now in between the layer and very small model, right? Cool. That's done. Well, let's do this also then. Okay, what is this? SM, what? Okay, okay, okay. Oh, we're here. Sorry. Let's try this out then. Now let's try create a deeper model that is much longer model. So I will just show you the architecture and I'll do the training right itself. I will not be going through the whole thing. Okay. You have, this is basically like 25 of these guys and then 5 of these guys and then 3 of these guys and finally is just one. So this is the architecture, 25 of these, 5 of these, 3 of these and 1 of these. Now how many parameters would be there? 25 into 5 plus 5 into 3 plus 3 into 1. That's the amount of parameters you will have in total. Okay, go inside sequence, you're adding every single one. I will just show you once the model state. That's it. Model nn, right? Nn dot state date. Okay, you can see for yourself. There's a lot of things happening here. If I can, I don't know if how this model. Okay, I have to run this whole thing right. This is great. Okay, then model underscore nn dot stat state date. There it goes. Oh, that looks pretty big. Okay, these are the 25 comma 5. Of course 25 of them are there in the 5 for the first, and then the hidden layer, basically the first hidden layer, and this is your 5 comma 3 and the finally 3 of them, 3 comma 1, right? Okay, cool. Okay, that is it. Let's go inside. Okay, stepping in, doing all the training is done. It will be done in a time. By that time I will just do this also so that I will have a good plot. And the training is done. And okay, where's the plot, man? Okay, this is the plot for the kind of deepish model, which is a bigger model. Seems the same to me. Cool. Works. Let's see how both of them compare to each other. Okay, it's a basic comparison. So logistic training, 3-layer model, that was the first model that we built, and then 3-layer network, right? Sorry, 3-layer is the second one that we built, right? So the logistic training and the 3-layer network is the later one that we built, the first one and the second one basically. And how are they comparing with each other in the training process and in the validation process? It almost looks the same to me, to be frank. Nothing crazy here happening. Okay. Okay, I can show you a few things. This is pretty cool. Okay, check this out. We are gonna look into the model a little bit, or the 3-layer model that we had. This is the first guy, so I can say W, and then okay, I already showed you all these stuff. You detach it that is, it is out of the whole thing. So it required grad becomes 0, so it does not have anything. If you are even doing any operations on it, it will not be added to your computational graph. It's detached in a sense. Okay. W and then blah. See, that's yeah, something I have already shown you inside it, right? I can show the shape of it as well. Blah blah blah. Okay, I have to do this and then do this. 5 comma 25, 3 comma 5, and 1 comma 3. Cool. Works because we are transposing it, that why it's become 25 comma 5, we're from the architecture I just showed you. 25 comma 5 and then 5 comma 3 and some. Okay, this is the NN equivalent of the whole thing. Now we can show the shape. This is how it looks like after everything happens. Okay. This is the network's forward propagation. This is how it look like after the power propagation. Yeah, and then putting it the logic, and if you pass through it, this is what it looks like, and the shape is something like this. Cool. Works. Mm. Mm. Yeah, these are the basically there are the weights you are comparing. How is the weights there are in the how the weights have really changed in the first model and second models, and you can see the values. So nothing really crazy here either. Oh, okay, I guess this is enough for now. We will be going on with activation functions, like all these activation functions like ReLU and all that, and kind of a deepish model with those activation functions that will give us a better idea of how things are working, and you will have a better model because you are using activation function which introduces non-linearity in your data. We haven't talked about it, I guess, so we will look into that in the next sessions. Okay, thank you.